a little bit better. So this is where we were at on Monday. So problem statement is, let me zoom in just a little bit here, is we have a system. All right, this is probably the simplest system we'll see for a lead controller design, just to start off, the first example here. And we're trying to build a lead controller to control the system. We want to have certain specifications. So since the design lead controller, since the overshoot is less than 20% and the rise time is less than 0.3 seconds. And so oftentimes we want to figure out, all right, will just the simplest control system possible, like proportional control, achieve this? And so that's what the very first part that we started on Monday was. We're going to just finish that up really quick and then get into lead control. So this is coming from Monday. These constraints, or these design criteria, translates to zeta is greater than 0.45 and a natural frequency greater than 6 radians per second. So on Monday's class, we had a blank area which should have been a blank grid. And so now we have this blank grid here. We can make this drawing a little bit more accurate. So the rise time constraint then turns into a natural frequency constraint. That's this arc here. And then a zeta greater than 0.45 corresponds to, we don't have exactly 0.45 on here, but we have something close, so we can kind of interpolate between the lines here. A ray coming from about here to the origin, and here to the origin. Okay, so we want both of these to be greater, so we're really talking about making sure our closed loop poles of our system are in this region. Right? That's what design constraints are telling us. And so then that's just mapping out the plane and trying to understand where we want the closed loop poles to be. And now step 2 would be looking and say, all right, would regular proportional control allow us to ever place closed loop poles here? That's one of the assessments we want to make. And so we can do this by plotting the root locus for this specific example. This one I did very, very quickly before we adjourn on Monday. I will go through it a little bit more carefully right now. So this is, with our system here, we have an open loop system. This is G of S. We have 2 poles, 0 zeros. Right? And so going back to what we've gone through the last few weeks about the relationship between the difference between the number of poles and zeros, we know that a 0 will attract a branch of the root locus. There are no zeros in this problem. So that means that the 2 branches of the root locus will go off to infinity. Right? And we also know from previous lectures that the asymptotes of these will be at plus and minus 90 degrees. Right, and so that's from just this discussion of these topologies, that if we have n minus m is equal to 2, then we have asymptotes that go off at plus or minus 90. Right? Or rule 3, if you want to go by the rules, but also we learned this kind of shortcut in terms of the difference between the number of poles and zeros and how we draw the asymptotes. Okay, intersection point. So intersection point is given by the summation of all the 0 locations minus summation of all the pole locations. Divided by m by n minus n. So this we have no zeros, so that summation goes all the way to 0. We have then poles at 0 and -1. And then m minus n is equal to -2. So this gives us a intercept location of -1/2. Right? And from here, actually, all the other rules don't necessarily apply to this. So we will try and look at this and try to understand what is the root locus plot for this system here, we, just like before, we draw our open loop poles and zeros on the plot. So we have a pole at 0, we have a pole at -1. We know we're going to have an asymptote going in plus or minus 90 degrees with an intercept location of -1/2. So that's splitting the difference between these two poles. Okay, then also given rule 5, root locus on real axis, we know the root locus is to the left of an odd number of poles and zeros, so that means that this space in between is the root locus as well. Okay, so we have to interpret what these lines mean, right? So the lines give us all the possible closed loop pole locations as we vary this parameter. In this case, it's the proportional gain from 0 to infinity, right? So that's for all possible options of proportional gain. And so what this is saying, green doesn't show up too well. Hope you can still see it in the back. What this is saying is that when k is low, the closed loop poles are going to be very close to the open loop poles, so somewhere in here. As I increase the gain k, the two poles are going to split, and they're going to go along these lines here off to infinity. So as I increase k, we go from having 2 real poles to now 2 repeated real poles, and then also then the split complex conjugate poles. As we increase k, it's going to continue to not change the decay rate, but the natural frequency is going to go up, and also the overshoot, all those other things are going to go up as we continue to increase k. So then the question is, will proportional control ever achieve closed loop poles in this region? And the assessment you should be making here, we can talk about more complicated ones if we get to examples like that, but the simple assessment here is that this green line, the root locus, never intersects the region of the closed loop plane where we want the poles to be in. So with a simple proportional controller, we cannot achieve the metrics. So this is a pretty easy way via this graphical method called the root locus to understand, all right, will proportional control ever get me there, or do I need to do something more complicated? So in this case, the answer is no. Proportional controller will never get you there because we cannot select the gain KP such that our closed loop poles are in this region. That's not a possible solution. Yes?
Are you saying specifically for this transfer function?
For this transfer function. Yeah. So there are plenty of examples where proportional controller, I mean, and also for these specifications, right? You know, if these specifications were such that I didn't care about overshoot so much, this line bends way over here, you would see that there was like an area where this peaks in, right? If we were to move this. So that's only for this specific example, which is transfer function and performance criteria. Right? Other examples of performance criteria that are whole. There's plenty of examples where proportional controller will achieve the performance you want. Yes?
If we did add like a KD and KI kind of KD terms, would it still be the same thing? Because like, can those be simplified into a game that is still like a K?
You're excellent at segues to the next material. Okay. It's like the fourth time. So you should keep on asking questions, but this is like every time you ask a question, like to the next thing. So yeah. And that's what we're going to talk about next. It's not going to be proportional derivative. It's going to be something called lead controller. We're going to show how, all right, we said that this shape of this root locus is not sufficient to ever place the closed loop poles in this location. We're going to talk about how we can morph the shape of the root locus by tuning other gains in this. Okay, where's my step 3? Okay, so the main message here, just for your notes, So given that the root locus does not intersect the desired location for the closed loop system, system poles, proportional control is insufficient to meet design criteria. All right, so then we have to do something about that, right? Okay, so what we're going to do is we're going to be modifying. We have additional gains that we can play with here, and we're going to, or additional terms that we can play with here, we're going to actually force the root locus to go through a location that we want it to go through. And so then the first thing I want to point out in terms of how we can make this root locus plot change is one thing that we can do, and I think you can see this from this plot, is probably one of our major deficiencies of why this doesn't work, is that the intercept of our asymptote is just too far to the right. Right? And so we can do things to make this intercept move to the left. So we want to force sigma A to the left. Okay. And so if we look at how sigma A is determined, it's determined by this equation. And so since we only have poles in here, the intercept is just essentially the mean of all the poles. When we have poles and zeros, it's no longer the mean of them because zeros add and poles subtract. Right? But what we can see is if we make a pole, we add a pole in here, such that the pole is more to the left than the zeros locations, it's going to drag this intercept towards the left, right? Which is going to put us in a better position to have this root locus plot go through this region. Okay, so if we look at these subtract here, keep in mind there's always going to be a negative in this denominator, but if we have a pole farther to the left than our zero, this intercept is going to go to the left. So that's going to be one element of this strategy. So adding a pole and zero pair, that is where the pole is larger in magnitude, will drag asymptote sigma A to the left. Okay, so what that means, we say adding a pole and zero pair, what that means is we are adding to the system, instead of saying that we just have a simple proportional controller, which is what we had before, we're saying that we have a gain on our system that we can modify. We have then a pole zero pair that we're going to add to our system. And so before we said a simple proportional gain, here we are making a dynamic compensator or controller, G1. So this has dynamics associated with it. It's now going from input air to output input to the plant. This has a differential equation associated with it, as opposed to just a static gain on the system. And we call this form a lead controller. This then goes to our plant, 1 over S plus 1. This is G2. C. And then this closes the loop. So then, so what we're doing is we're adding dynamics to the system. This is required if we want to bend this root locus plot farther to the left. And then if we want to put this in the context of how we always look at the root locus plot, what we do is we say, all right, there's a single term k that we're going to vary from 0 to infinity, and then there's going to be everything that has dynamics associated, we're going to lump into the single term g. So what that means, I'll get to step 1 in a second because I ran myself out of space. Here's our gain k that we're going to vary from 0 to infinity. And everything that has dynamics associated with it, we're going to lump into a single transfer function. Which we're going to call g. So just as a quick aside here, what we're doing, this is more mathematical that we're lumping these together, right? So keep in mind, G2 represents the plant. So this would be something physical. This would be something you can sit at your desk or in a manufacturing facility, wherever you are, right? So we're mathematically lumping this with the compensator or controller, which is the dynamic portion of the lead controller, which is usually something in software, right? So we're mathematically lumping something that's virtual and physical, but keep in mind that these are hardware-wise are two completely different entities. Okay, so any questions about that idea before we get into the rest of this problem? Okay. All right, so step 1. For design, choose closed loop pull. Such that design criteria is satisfied. Okay, so some recommendations here. So here's where the design portion comes in, where we have a lot of freedom to choose pull locations and a lot of other terms. And so there's going to be a lot of questions about, okay, what are good choices for these closed loop pull locations, right? And so this is, it has a little bit of a learning curve associated with it. My rule of thumb here is that if your boss asks you to, this is not a good rule of thumb for everything else in life, but for control design, this is a good rule of thumb. If your boss asks you to have certain design criteria for a closed loop system, you want to do that, but just barely. You do not want to exert any more effort than that. And so we'll talk about that in a second, but we're talking about the easiest location for us to put the closed loop pull locations is in this corner here. So the farther that I try and push closed loop pull locations, say move them to the real axis, that means considerably higher gains in our system, which corresponds to a bunch of negative effects such as noise amplification, et cetera, that was going to make it difficult for you to design controllers even theoretically, but practically speaking, it's going to cause a lot of issues as well. So really what we're trying to do is we want, all right, so your boss says it has to satisfy these two design criteria, put it in this corner, and this is going to be our desired closed loop pull location. So we're just barely satisfying his or her request for what the closed loop pull location should be, right? That's my recommendation. The other recommendation is to choose nice round numbers. So you don't say, try to parse this out and say, well, this looks like negative 3.3 plus 5.25i for that closed loop pull location. For this example, we're going to choose negative 4 plus 6i as our closed loop pull location. All right, so we're going to choose a closed loop pull location that we're going to then force the root locus to go through, is what the strategy here is. All right, so make it easier on yourself. Make it easier on the graders when they're working on these things to choose nice round numbers, etc. here. So for this example, we're going to choose S is equal to negative 4 plus 6i. There's nice integer values here. All right, so now we need to make sure the root locus goes through. So what we're attempting to do in a really brief sketch is we have the poles of our plant. Those don't go away. Those will always be there. We can't do anything about those. Those are fixed. Is adding a compensation so that when it's going to put a portion of the root locus between here and here. So by dragging the asymptote to the left, oops, I somehow deleted all that. When the portion of root locus here breaks away from the real axis, instead of going along this asymptote here with this intersection, it's now going to go along an asymptote moved farther to the left. So by adding this pole and 0, I have distorted the root locus plot in a way that's favorable for us in terms of creating a controller. Any questions about that idea? Yes?
What does a lead controller actually mean? What kind of the code of it, or what is its physical? What is a pole and 0 as far as software goes?
Okay. Yeah. So the best analogy that I have for this is that a proportional derivative controller and a lead controller are essentially interchangeable. Okay, so a lead controller is an approximation of the idea of a proportional derivative controller. So then, I don't know if you were here on Monday, but there was a discussion about proportional derivative controllers don't technically exist. You can't actually build one. Every single proportional derivative controller is a filtered proportional derivative controller. And that's exactly a lead controller. So we use the term proportional derivative because that's really intuitive and that's what the industry calls it, but that's not, it's a little bit of a lie. It's not technically a proportional derivative controller. So this now we're saying, let's now unmask that idea of there being a filtered derivative, and so let's look at moving the poles and zeros around and use the full thing. If that makes sense. Yeah. So it'd be like a PD controller essentially. Yes, Carson.
So wouldn't you want to move that way far to the left so it doesn't oscillate too much? So just make it more like -1 billion and make the 0 0.
So -1 billion, that would be getting back to PD control, right? So if we look at the pole location determines our filter, what frequency we filter, so that would be like having a really high gain feedback with no filtering at all. So that's going to cause you, okay, so in terms of mathematically, you can definitely do that. That's perfectly legal. In practical aspects, that's going to cause a lot of oscillation to the system as you're no longer filtering that derivative, which can have negative effects on noise. So that's kind of beyond the scope of this class, which is more theoretical, but practically that would not work very well. Yeah. Ben? Exactly. So this is just hypothetical right now. We're gonna put some actual numbers on this in a second. All right. So step 2, design PC and ZC to achieve this. This is designing your pole and 0 location. And so this is starting off first with a rule of thumb. Like every other semester I've taught this, all students were going to hate this rule of thumb because this is, of the rules of thumb, it's probably one of the more wishy-washy of the rules of thumb, but the general rule of thumb is to place ZC approximately equal to omega n desired, right? And then from there, calculate PC to ensure root locus goes through the correct point. Okay. So what we're going to do is we have now 3 variables to tune, and we only have, basically there's an infinite number of solutions for the pole and 0 location that will cause it to go through our point -4 plus 6i. And so since there's an infinite number of solutions, we need to pick one so we can then uniquely solve for the other unknown variable. So it's like having 2 unknowns, 1 equation, right? So we're going to set one of these, and we're going to follow a rule of thumb to set that. And so basically what we're going to say is that the ZC is approximately equal to the natural frequency desired. So going back to the problem statement or the really early work that we did here, we said that omega n desired was 6 radians per second. So we are going to select the 0 location to be equal to 6 radians per second. Okay, so that means we have plant is fixed, ZC we have selected as 6, and now what we're trying to, yes, Tyler.
Our mega n was in 4 or?
It was 6. Yeah. So then the remaining thing to do now is we're trying to understand, this is 6, we're trying to understand what value of PC or pole location will ensure that somewhere on this root locus it intersects this point, which we specified as -4 plus 6i. All right. And so we can actually do this. If we have a ZC selected, we can make sure it with 100% certainty goes to that point. And so this is coming directly from the angle criteria that we've learned in previous classes. So the angle criteria, as a reminder, is that if we have some sort of test point, S, and this test point is on the root locus, then we'll have the property that the summation of all the angles of vectors running from the 0 locations to that test point minus the summation of all the angles of vectors going from the pole locations to that test point has to be equal to 180 degrees or some 360 degree rotation of 180 degrees. So we're going to use this directly. So this is one of the rules in which the root locus is defined for. And so what this means graphically is that this is a vector going from my 0 to that point, and I can call this a, what did I label this? Theta 2. All right, this is a vector going from this unknown pole location. So we don't know what PC is yet, but we can write and say, all right, this would be, we can label this and call this is theta 1. We can calculate theta 2. We can also calculate what we will call theta 3, which is a vector running from this pole. Oh, that's terrible. At -1 and the pole at the origin. And we'll call these poles theta 3, or call these angles theta 3 and theta 4. Okay, so using this equation, then we have that theta 2 minus theta 1 plus theta 3 plus theta 4 has to equal 180 degrees or some 360 degree multiple of 180 degrees. Yes? Yeah. It doesn't matter. Just A has to be an integer. Yeah. As long as A is an integer, this works. Yeah. So 0 being an integer would be, so it depends on whether you count from 1 or 0. Okay. So we know theta 2, theta 3, theta 4, and so now we just need to solve for theta 1. So rearranging this equation, I get theta 1 is equal to theta 2 minus theta 3 plus theta 4 minus 180 minus 360 degree multiples for some integer a. Right. Is our unknown angle. Okay, so I'm going to try and keep this all on one page so you can see this. This may not work out so well. Okay. So I have to just go back and forth here. All right, so we have our unknown theta 1. And it equals, first term is theta 2, right? So we can look at what theta 2 is. And if we look at and I drew this 0 slightly off, right? So this is 6. This angle looks like it's greater than 90 degrees, but actually would be less than 90 degrees because this is a rough sketch. But if I look at the vector going from this 0 to this pole location, this is at 6 on the real axis, and it's going to -4. So that means in terms of finding this angle, it's going to have a real direction of +2 and an imaginary direction of +6. So this first angle is going to be inverse tan 6 over 6 minus 4. Second angle is theta 3. That's the pole that's coming from the pole at -1. So this is going to have a real part of -3, because they're going -3 in the real axis. Imaginary part of 6. Oops. Missing the arctan function. Okay, so the last angle coming from the origin, real part of -4, imaginary part of +6. And then we have then minus 180, and for this example, we don't actually need those multiples to figure out what the solution is, but you can throw this in a calculator and you would get then 11.31 degrees here. Okay, so just kind of going back to what we did, very first homework in lecture 2, we talked about why you should be using the ATAN2 function in your calculator in MATLAB and not ATAN. That's because the arctan function will only output phase angles between +90 and -90. So you need to provide basically what is the sign on both the real part and the imaginary part to get this correct. Right? So these angles here, if you were to try and just put in what I have here is just the typical ATAN function in MATLAB, this is going to give you the wrong answer. So you need to use the ATAN2 function. So if you have not used that function before, I would take a look at basically the help files to understand how to use it, but that's going to be necessary to get these ones correct. Yeah. All right, so we have found unknown angle theta 1. So now we're good. We know this one. And then through geometry, we can determine what PC is. Right? So if we look at what this angle is, what we want to know is what is this length here? Because I already know that from here to the origin is -4, so I need to figure out what this unknown length is. So this is just using geometry and trig. So I know that theta 1, or tan theta 1, is equal to 6, this unknown PC minus 4, or I can rearrange this equation and get that PC is equal to 6 over tan theta 1 plus 4, which is equal to 34 radians per second. Okay. Any question about what I did there? Okay, so what this tells us is that our lead controller, we're almost there. We have, of the 3 variables of our lead controller, we figured out 2 of them. is designed to be k over s plus 6, sorry, k times s plus 6 over s plus 34. Right. And we'll show on Friday's class how this forced the root locus to go directly through our desired point. And we'll also show how we get and figure out then this unknown k value. Right here, this is still unknown. But we can uniquely solve for this, and we can uniquely solve for this just like how we looked at what are the k values that keeps the system stable, or what k value is the k critical, which the system becomes unstable. All right, so we'll get to that on Friday, but in the last minute here, any questions about what we've done here today? Okay, see you on Friday then.